Hello again, folks. So here's our first lesson on Newton-Raphson, which is a formula for getting iterative formulae. These are the things we need to be able to do. Use it to find a root of an equation. We'll do that in a minute. Represent it on a graph. That's what we'll do next time. And we continue to need to understand that all iterations don't converge to a particular root. And we'll see more about how Newton-Raphson fails in the next lesson. So the long and short of it is that's the formula. It's given to you in the exam. This is exactly how it appears in the exam, except that's next to the colon. And we just need, given our equation f of x equals 0, to plug that in here, f of x, replacing x with xn. We need to know the derivative of f of x, so we'll have to differentiate f of x. We'll put that here, and then we've got a formula that we can use for iteration. It's that simple. And it works, it's really reliable, so long as you're quite near the root. It works cunningly, essentially by saying, well, if I'm really near the root, the graph basically looks like a straight line. Where would a straight line from here cross the x-axis? And that gives us a really good approximation really quickly in very few steps. So we'll see more about how it works on a graph and looking at that approximation using a straight line next time. But for now, let's just look at a question. Here's the sort of thing you might get asked in the exam. Given this function, I want to show that the function equals 0, so this equation has a root between 0 and 1. 2 marks. You know that you need to write some stuff as well as working out f of 0 and f of 1. Using x equals 1, it's the first approximation using the Newton-Raphson method 3 times. So we're going to write out this formula replacing f of xn with this, with xn in it. We're going to differentiate f of x in a second and put it there. And then we'll have a formula which we'll apply 3 times to get 3 better approximations to the root, just like we do when we're doing fixed point iteration, and we have an iterative formula there. And then that third one is the final approximation they're referring to there. So the last approximation we get, we'll round to 4 decimal places, and we'll show that that actually is the same as what the root would be to 4 decimal places if we knew the real root. Okay, so let's get cracking. You can stop it and have a go and then check if you like, or you can just follow through. So follow me along with me. So here's f of x, and part A, hopefully you're happy you're working at f of 0 and f of 1. I get 1 and minus 1, and I state, oh, there's a change of sign, therefore there's a root in the interval. You need to say there's a change of sign, you need to say, and that means there's a root in the interval. And if you don't say both those things and link them together with a so or a therefore, you're not going to get the second mark for that part. Okay, we need to work out our Newton-Raphson formula for this function. So using this formula, we're going to plug f of x in on the top. I need to know f dash of x, so that's the next thing I'll do. For part B, I'll differentiate f of x and write down f dash of x. Hopefully you agree with that. Then I'm just going to write my formula out. So xn plus 1 is xn, the previous number. Take away this fraction, and I just write that out with f of x on the top and f dash of x on the bottom. And notice all of the x's have now got a little n next to them to say that's my previous number. So when we put this into the calculator, the xn's get replaced with the ands key, don't they? Okay, so let's do that. x0 is 1, so 1 equals. I'm gonna type in my formula using the ands key then. So clear. xn is ands minus, I need a nice big fraction, ands to the power of 5. I need to use the arrow key to go across there to get back on the main line. Minus ands to the power of 4. Same again. Minus 2 ands cubed plus 1. So that's f of x on the top. On the bottom, 5 ands x to the 4 minus 4 ands cubed minus 6 ands squared. Okay, and I just hit equals, and it gives me my x1, 0.8. Get my calculator back, hit equals again. That's my x2. So I'll write that down, and hit equals again. There's my x3. So we'll write that one down over there on my page. And there you go, we've used it 3 times to get 3 more approximations. We've done part B. Let's move on and look at part C. So I'll write out x3 again. And for part C, they wanted us to show it's accurate to 4 decimal places. So this value for x3 rounds to that to 4 decimal places. So we're saying the root also rounds to that to 4 decimal places. How do we check that? You know this, it's with a change of sign. We need to go half of one of these either way. So half of a 10,000th either way, because we're saying it rounds to this, not to 0.7716 and not to 0.7718. We need to go halfway to each of those. So those are the numbers we're plugging in. When you put them in, you get these numbers, one positive, one negative. You don't need to write a lot of detail. You do need to write the number. It would probably be nice to say greater than 0 here and less than 0 there. Make it really clear that they're one positive, one negative. But essentially, you then say there's a change of sign, so there's a root in that interval. And so the root is that to 4dp. Job done. Okay, so to recap, this is your formula, and as long as you can differentiate the function you've got, you can write out the formula and you can use it. Jobs are good, and it works nice and quickly. We'll talk about comparing it to fixed point iteration, why we need both, the pros and cons of either, and of course representing Newton-Raphson on a graph next time. But for now, crack on with the questions. Thanks, bye.